Okay, welcome to the first screencast on series connections. We're talking about putting multiple electrical elements together, like multiple light bulbs or multiple resistors or other groups of several different things. The key to a series connection is that your circuit will only have one path. So from the high potential point of the negative terminal of the battery or power supply to the positive terminal at the low potential, you should only be able to trace one path for the electron to travel. Since there's only one path, then there's no other place for the electrons to go, and it's always again going to move from higher to lower potential. And since there's only one path, their current is a fundamental property of matter. Charge is a fundamental property of matter, and current is based on moving charge. So you must have the same current. The same charge must pass the same spot, any spot, all the time throughout the circuit. Okay, now the potential difference will be different. It will be based on the size and the resistance of the various materials. Larger resistors, larger light bulbs with higher resistance will use more potential difference because they'll need that energy to work. And then finally, one big concept is the loop rule. Okay, so as you go around the loop, and in a series circuit there's only one way to go, all of the potential difference, all the energy we put in essentially, will be equal to all the potential difference drops or losses as we go around the circuit. Okay, so let's try to apply that to this first question here. I've got two diagrams, and I'm trying to figure out the potential difference at spot that I don't know here. Now, I'm putting in 120 volts, so my potential difference, my potential at this high point is 120 volts. As I go through the wires, I don't lose anything. As I go across here, I'm going to have a loss, and it's going to be a potential drop. Over here on the other side, I can see that I have a potential drop of 80. And notice it's negative. They're showing us that it's a drop, a loss of energy. Now I put in 120. I lost 80 over here, so that leaves 40 to drop here. So if we take the 120 volts that we put in, and we subtract from that the two light bulb potential differences, then they should add up to 0, because whatever we put in needs to be equal to whatever we take away. So if you want, you can create an equation with that. You can just kind of try to think it through. You can use ratios often, like in this case, the light bulb on the bottom used twice as much potential difference as the one on the top. That's an indication that the light bulb on the bottom has twice as much resistance as the one on the top. Okay, and this one on the right, we're putting in 12 volts this time, 10 times less. Again, that's high potential right here at the battery, at the negative terminal of the battery. As we go across this first light bulb, we're losing 3. So another way to do this is kind of keep track of your potential. So here we were 12. We went across here, we lost 3, so now we're down to 9. We go across this one, we're going to get to some other number. We don't know that one yet, that's our unknown. We go down here, and we will have dropped off 4 more. Well, we have 9 here. Well, we're going to lose 4 over here, so we must make up the difference in this spot right here. And so that would appear to be -5. Now we can always check ourselves. If we put in 12 volts, and then we take away all the other potential drops. 3 plus 5 is 8, minus 4 more is going to be 12. So 12 minus 12 equals 0. Check. We're good to go. Alright, so that's true for any one loop of a circuit. And any DC circuit will always be that way. It's one of Kirchhoff's rules, the loop rule. Okay, so here we're again just checking that idea of where the potential will be highest, where it will be lowest. We're just going to do a quick comparison. In the series circuit, we only have the one loop, so I can trace only one pathway as I go around. So if I start the negative terminal and follow an electron, one path, only one path, no junctions, no places for the current to split off. So that answers this question here at the bottom right away. They all have to be equal. There's no place for that current to go and change, so it's going to be the same everywhere. Then the potential is always going to be highest at the point where it leaves, where the charge leaves the battery. Okay, we have lifted it up given the electron's energy, the charge energy. And then it'll stay the same as you move through wires. We're going to assume they have zero resistance. But then as we go across from F to D, we're going to give up some of that energy. So D would be less than F. And then we go through here. Again, through the wire, we're okay. We don't lose anything. But as we go across the light bulb, we're going to lose some. Then we go to C. Between here and here, we're not losing anything. But between D and C, we definitely will have lost. And then we get here, we go across the light bulb, second light bulb, where we're going to lose more. And in fact, by now, we should be at zero. So both of these should be essentially zero potential. So A is always going to be less than anything else, and A is less than G. A is the point of low or zero potential, and G is the point of high potential. And again, electrons will always go from high potential to low potential. Just like a ball will always fall, it will drop from a higher position in a gravity field to a lower position. In terms of B and C, again, as we go across there, we're going from C to B, we're going to lose, and B again is essentially zero. And then this one as well, B is essentially zero, so it has to be less. Now over here, we flip the battery over, so we're going to kind of go in the other direction. But the label, the lettering is essentially going the same way. So in this time the lettering's going in the opposite direction. So A is our highest point of potential, and F is going to be our lowest. Since F is our lowest, everything else except point D is connected directly by a wire. So there's no change between those 2 points. B to C, we're actually lose potential in 2 places. So B is definitely going to be higher than C. And then A compared to F, of course, A is the highest point and F is the lowest point. And again, as I go around there, there's only one path. So these currents must, in a series circuit, always be equal. Alright, so we'll wrap it up with a couple of other things that come out of series circuits. When you're trying to find the total or equivalent resistance of a group of objects connected together in series, when you put them in series, you're essentially making the circuit longer, which makes the resistance go up. So it is just going to be the sum, the addition of all the resistors. So if I have 2 4-ohm resistors, I would simply add them together, and I would get 8 ohms. If I have 3 4-ohm resistors, then 4 plus 4 plus 4 is 12 ohms. If I have a 4 and a 6, that makes 10. Add another 10, and we're up to 20 ohms. Okay, so just add them together. It's very straightforward. The following statement is definitely false. You have the light bulbs connected in series, and one of them goes out. This says the brightness will be noticeably less. Well, it's not just they're not going to stay lit with less brightness. As soon as you break the electric field in any part of the circuit, you are going to have the whole circuit go out. So let's go back up and take a look at one of these pictures. Sometimes I get the sense that people think, well, the electric current can at least travel to the point where the break is. So say this light bulb goes bad. That's a break in the electric field. It's not that the electric field goes to here and stops. Again, from our very first activity, to have an electric current flow, there must be a complete path for that electric field to set up. So in series, if you have anything go wrong with any of your devices, it's going to shut down the whole circuit. So typically that means when you want to put in a switch to turn things on and off, you'll want to put it in series with the things you're trying to turn on and off, so that it can break the electric field and make that happen. Okay, well, that's our first beginning of series. We'll look at some other circuits next and make sure we're all clear on that.